So let's do one example. Like I mentioned, it's going to be a gravitational field between two objects, one of them being Earth. So let's start with drawing a picture. So let's say this is our Earth, okay, and we want to calculate the gravitational. So I'm going to write Earth here. And then we're going to calculate the gravitational force between Earth and, let's say, an object here. Pardon? You can't see my screen? Okay, sorry about that. No problem. So in this example, we're considering two objects and their gravitational force between them. The first object being Earth. So this is our Earth, and we want to calculate the force of gravity using the universal gravitational law formula between Earth and, let's say, another object we have a little bit far from Earth, let's say here. Well, just for the purpose of our example, I'm going to draw it a little bit further so we can see it, but the distance is not going to be that high. Let's say this is an airplane. Okay, this is an example. And we're going to calculate how much is the force of gravity between these two objects. We talked about the gravitational, so universal law of the universal law of gravity, or universal law of gravitation, basically simply comes down to this formula of saying there is a force of gravity. Okay, so I should say the name of the law is gravitational. The force of gravitational, the force of gravity between any two objects that exist in the universe is equal to the number g, which is a constant number, times mass of object number 1 times mass of object number 2 divided by the distance between them squared. This is the universal law of gravitational formula, and the concept is that any two objects with mass m1 and m2 with a distance r, they apply a force of attraction towards each other, which could be calculated using this equation. So the first thing we notice, and the first thing that we need to consider, is that this force comes as a pair. It means they're both objects attracting each other at the same time. So they're both applying Fg on each other. The amount of force Fg that they're attracting each other with is exactly equal. But for the purpose of our example, I'm just going to name them differently. But we know that Fg1 and Fg2 are equal because they're attracting towards each other with the same force. Okay, so airplane is attracting Earth, and Earth is attracting airplane at the same time with the same force. Any questions so far? Okay, now how much is that force? That force is equal to, so first we have to write down our information. So we need a mass of number 1, which is the mass of Earth. We are going to assume that is equal to 10 times 10 to the power of 24. Correct? We said roughly it's equal to 6 times 10 to the power of 24. So that's the mass of Earth, M1. So I'm just going to write here that M1 is Earth. And so mass of object number 2, let's make an assumption for that too. So what do you think the mass of an airplane is going to be? Let's say there are not very large airplanes, let's say average or small airplane, 100 people inside. So 100 times average of person, let's say 750, 7,500 kilograms, so 7,500 kilograms. And the mass of airplane altogether, let's just assume 5,000 kilograms, okay? Sorry, not 5,000. 5,000 is very low. 5 times 10 to the power of 6 kilograms, okay? I'm just making an assumption. It could be very wild assumption, but we're just doing the calculations. Now the radius, the distance between the two objects. What is the distance between two objects? What do you think? So here I'm going to talk about r. What is the distance between Earth and airplane? First of all, how do we calculate the distance? What does it mean by distance? Also, how much is it? The distance between two objects, based on the definition of physics, is the distance between the center of one to the center of the other one. That is defined as the distance between two objects. Now, we need to know two things. First of all, we need to know the distance between airplane and the surface of Earth, which we can calculate probably. Another thing we need to calculate is the radius of Earth. Okay, that is also a factor here. Correct? The radius of Earth, it means this distance from here to here, is equal to 6,000 kilometers. 6,000 kilometers. Again, roughly. So there's obviously it's not exactly 60,000 kilometers, but I put one. 6,000. Yeah, but roughly we can say it's equal to 6,000 kilometers. Okay. So now we need the distance from here to here too. So how much do you think that distance is? Again, we're going with the calculations, but I just want to quickly search height of airplane on Google, and it gives me the altitude of so 30,000 feet, 1,000 meter, so like 1 kilometer. Okay, let's just assume that this is also 1 kilometer, which is also very high in number, but let's just assume that. Okay, so far okay. So the distance between airplane to surface of Earth is 1 kilometer, 1,000 meter high. And also the distance between the surface of Earth to the center of Earth, it's the radius, which is 6,000 kilometers. So what's the distance between Earth and airplane? The total distance? 6,001 kilometers, correct? Okay. And what is G? So this is another thing that we have in our equation. The constant G is also equal to 6.67. This is given, or we can just look it up. It's called the gravitational constant. It's in the equation of our gravitational law, universal law. So that's 6.67 times 10 to the power of negative 11. And the unit is Newton meter square divided by kilogram square. This just means that all our other units must be kilograms and meters. So this means we have to convert this 6,000 kilometer, which is also 6 times 10 to the power of 3 kilometers, to meters, which would be 6 times 10 to the power of 6 meters. Okay, any questions so far? All right. So now I think we have everything we need to calculate Fg. What is Fg again? It's the force that Earth and airplane, both of them, apply on each other at the same time with the same quantity. Opposite direction though. They're attracting each other. One is towards left, one is towards right. We're going to talk about that as well. Okay? So now let's calculate it. Fg is equal to G times M1 times M2 divided by R2. Okay? Sorry, this is M squared M2. Okay? So I quickly check. Do I know what is G? Yes, I know it's 6.6. Do I know M1? Yes, M1 is the mass of Earth. Do I know R? It's the radius of Earth. Okay? Now, something interesting happens here. When I look at this equation, G is always 6.67. M1, when Earth is in the equation, when we're comparing the force of gravity between Earth and something else, the mass of Earth is always going to be mass of Earth. That's also not going to change. Correct? So the value of G and the value of M1, whenever we're calculating the gravity of Earth, gravitational field between Earth and something else, okay? In this case, it's Earth and airplane. We could be doing Earth and me, Earth and an apple, Earth and a book. So Earth and something else. Mass 1 always going to be the mass of Earth. That's not going to change. G also is always 6.67 times 10 to the negative 11. So far, do you agree? Also, R doesn't change. Now I know that R is 6,001 kilometer here. But the distance between the Earth's surface to the object in compared to the radius of Earth is very low. Now, what is the radius of Earth? 6,000 kilometers. So now, what would you think the distance between Earth and you is? Remember, distance means center to center. So center of Earth to the center of you, center of your body. How much is that distance? 6,000 kilometers, which is the radius of Earth, plus something. Correct? What is that something? Give me a rough estimation. Do you understand my question? Okay. So the distance between you or airplane or any other object to Earth, how do we calculate that? That's very important. For example, the distance between airplane to Earth, or the distance between Earth and the book on your table, or the distance between Earth and my body or your body. How do you calculate that? So there are two components in it. First of all, we agreed that the distance between two objects is equal to the distance of center of object number 1 to the distance of center of object number 2. Do you agree with that? Okay. So therefore, the distance between Earth and my body is the distance between the center of Earth and the center of my body. Correct? Which is also equal to the distance, to the radius of Earth plus the distance of me to the surface of Earth, isn't it? So if I want to draw it very quickly in the side here, the distance between Earth and my body basically is equal to the radius of Earth plus the distance of me to the surface of Earth. Is that right? This amount, the distance, let's put it, this is the radius of Earth, and this little small is going to be the distance between me and surface of Earth. Do you agree or not? Okay, so now when I'm saying what's the distance between you and Earth, that's equal to the radius of Earth plus, give me a number, give me a rough estimation. What's the distance between you and the surface of Earth? Rough estimation. Center to center. So more of a, let's say, half of that would be. So if your height is, let's say, how tall is your height? So let's say 174, and then your center of body would be half of that. So it would be 174 divided by 2. So this distance means your center of body to the Earth is 172 centimeter divided by 74 divided by 2, which is equal to 87 centimeter. So the distance between you and Earth is equal to 6,000 plus 87 centimeter. And I have to convert centimeter to kilometer because it's 6,000 kilometer plus 0.000, and that's for meter, and then another 87, like that. So the point is, the distance between Earth and object, any object, airplane, your body, the book, the laptop, anything, any objects that we can imagine, the distance between Earth and that object is roughly equal to the radius of Earth. Because even though the distance between you or the object to the Earth is like a amount, maybe half a meter, 1 meter, 10 meter, whatever that is, but it's a very small amount of number. So the distance of objects between Earth and objects around Earth roughly is always equal to 6,000 kilometers. Do you agree with that? Even with our airplane, we calculate it's 6,001. So it's not a very big difference. Even when you're like writing it and rounding it down, you kind of ignore that 1 kilometer at the end. So the distance between object and the surface doesn't really affect our calculations a lot. Do you agree that far? Okay, so now what conclusion do we make from here? The conclusion is that when you're calculating the force of gravity between Earth and any other object, but Earth is one of the objects, okay? So one part of it is Earth, the other part is something else. In this case is airplane, it could be some other object. If that happens, the amount or the value for G is always constant. The value for M1 is always constant because that's mass of Earth. The value for R squared is always also constant as well. It's always 6,000, roughly. Because I know sometimes it's 6,001, sometimes it's 6,000 point something, but roughly we can say it's always equal to 6,000. Now, because G, M1, and R squared are roughly always the same number, someone came and said, okay, if these numbers are always supposed to be the same number, so why don't we just calculate them separately? It looks like in every equation, M2 is going to be the only mass that is going to be different. In this case, the mass is the mass of airplane. If you want to calculate the gravitational force between Earth and something else, let's say an apple, that everything will be the same. G would be the same, M1 would be the same, R squared would be the same, only M2 will be different, which would be the mass of apple. Right now is airplane, correct? Now someone said, if these three components of the equations are supposed to be always the same for problems that involve Earth, then let's calculate these numbers separately. And they calculated it, and it was equal to 9.81, our famous 9.81 that we use. So suddenly, the force of gravity only involving Earth. Remember, this is only if Earth is one of the objects. Suddenly our equation could become shorter. Fg equal to 9.81 times the mass, which is our famous mg. So this is where F equal to mg came from. Its original equation is the gravitational universal law of gravity. So that was the main equation, but because Earth has always the same mass, same distance, and g is always constant, someone came and said, okay, for all the equations of universal law of gravitational, if Earth is one part of it, instead of writing g m1 m2 over r squared, I calculated g m1 and r squared separately. It was equal to 9.81. So let's just use that number instead. And they called it g, the small g. That is why the force of gravity between two objects suddenly becomes Fg equal to mg, the equation that we used in Unit 1. So this basically is a special case or a special occasion when Earth is one part for the universal equation law. Okay? Let's go back to our calculation. Now, when we're looking at the equation and everything here, now we calculated g, m1, m2, and r squared, and we said that there are all these numbers, so let's write them down. Even though we know that we can use the short format f equal to mg, but we're going to stick with the original equation. Okay? Let's say we don't want to use that that law we just explained and talked on the left side. I just wanted to say that because that's our next topic. We're talking about where g came from. So the small g came from here, the mass of Earth and the radius of Earth. But now going back to our equation, our question, we want to calculate the force of gravity between airplane and Earth. So g is 6.67. I'm following our gravitational equation times 10 to the power of negative 11. m1 is equal to 6 times 10 to the power of 24. And then m2 is equal to 5 times 10 to the power of 6. They're all in kilograms. Divided by, excuse me, the radius to the power of 2. Radius was 6 times 10 to the power of 6, and that is to the power of 2. Okay, any questions? Okay, so now what we do is, okay, first of all, everything on the top, we will have, I'm doing a very rough, again, calculation quickly without the calculator. So 5 times 6 times, so 7 times 6 is 42 times 5 is roughly 200. So I'm just doing numbers. That's roughly 200. 10 to the power of negative 11 times 10 to the power of 24 and 10 to the power of 10 to the power of 6 is equal to 30 minus 11, 20, 19. So times 10 to the power of 19. What do we have in the bottom? We have 6 times 10 to the power of 6 to the power of 2, which is equal to 36 times 10 to the power of 12. Okay, again, I'm doing very quick calculation without using the calculator. We just want to go through the process. So 200 divided by 36, it's roughly equal to 6. Again, 5 point something. And 10 to the power of 19 divided by 10 to the power of 12, again, is equal to 10 to the power of 7 Newton. So this is the force. Again, roughly. All our calculations were very quick and roughly, but that is the gravitational force being applied to airplane and Earth based on our example. Do you have any questions? Okay. Everything is clear? Now we enter the second part, which is very important. So Now we know Fg, which is the gravitational force between Earth and airplane, is equal to 6 times 10 to the power 7 Newton. I mean, roughly, because everything from the beginning we were assuming. The mass of Earth, we rounded up. The mass of airplane, we rounded up. The distance, we rounded up. Everything we did quickly to go through the process. So roughly, the force of gravity is 6.10 to the power 7 newtons. And we said that that force applies on both objects, one to the left, one to the right. Okay? So it means Earth is pulling airplane with a force of 6 times 10 to the power of 7. Airplane is also pulling Earth with the force of 6 times 10 to the power of 7. So now the question is, if airplane is pulling Earth, how come Earth is not moving? Earth is also pulling airplane, and we know that is pulling it towards it. I mean, if the engines of the airplane shuts down, we will see that the Earth will attract airplane with a very large force, which is equal to 6.6 times 10 to the power of 7 Newton. But how come how come Earth is not moving towards airplane? If they're both applying the force against each other, how come only one of them is moving? Now, to answer that question, we have to kind of go back to our chapter 1 and 2. We're going to calculate how force moves objects. I'm going to briefly explain how. Basically, what we learned in chapter 1 was if there's force, that force is going to generate acceleration. And that acceleration is going to cause movements. Remember? So everything comes from force. Now we're going to talk about it here. Force applied on airplane, force applied on Earth. We agreed on this part. They're both applying force on each other. Same quantity, opposite direction. Now we're going to talk about how come Earth is pulling airplane, airplane is also pulling Earth, but how come only airplane is moving towards Earth, but Earth is not moving towards it? By the way, if Earth was supposed to move towards airplane, it would be a disaster because every object will pull Earth towards itself from different directions, and then if Earth was supposed to respond to it and move, then we will have a very shaky world. Now we're going to talk about why it's not moving. So airplane, we know that the force being applied on airplane is equal to 6 times 10 to the power 7. We also know, this is the force of gravity, we also know the force being applied on Earth is equal to also 6 times 10 to the power 7 newtons. The force is the same. So I'm going to try to kind of draw an airplane. Okay, something like that. So, and then I'm going to try to draw the Earth here. So now we are separating the cases. We're going to look at Earth and we're going to look at the airplane separately, right? So we agreed that there is a force pulling the airplane this way, and that force is equal to Fg. We also agreed that there is a force, the same force being applied on Earth, pulling it the other way, and it's also equal to Fg. The amount of force is the same. So now, what is the mass of airplane? Mass of airplane, we call it m2 in our, it's equal to 5 times 10 to the power 6. So this is where it becomes important. Now, there's a force of Fg, and there's a mass of 5 times 10 to the power 6. Can you find the acceleration? Yes, we can. F equal to ma, correct? So F is how much? 6 times 10 to the power 7. M is how much? 5 times 10 to the power 6 times acceleration. Acceleration becomes very high. Acceleration becomes around 11. We know acceleration 11 is very high. What does acceleration equal to 11 means? 11 meters per square second. It means in every second, this force and this acceleration is going to change the velocity by unit of 11. It means if the object was moving with the velocity of 0, 1 second later it's going to move by the velocity of 11. 2 seconds later it's going to move with the velocity of 22. The velocity is increasing by a factor of 11. Recalling the concept of acceleration from chapter 1 and 2, acceleration is how or the rate of change of velocity. How velocity is changing. Velocity in this case is changing by the factor of 11. It's ridiculously high. It means every 1 second, velocity becomes 11 more. If you imagine you're in a car and you're going with a velocity of, like, let's say 10 or 11, and then every 1 second you're increasing by 10, how much would it be after 10 seconds? How much would it be after 30 seconds? After 1 minute? It would be ridiculously high, right? So this is a very high acceleration, and we can see because the mass of airplane was 5 times 10 to the power 6, suddenly the acceleration of airplane becomes really high. It means that the force being applied on airplane is the same, 6 times 10 to the power of 7. But because the mass of airplane is smaller, then the acceleration is 11. Now let's calculate the acceleration of Earth. Mass of Earth is 6 times 10 to the power of 24 kilograms. Now, the force being applied on Earth, again, same thing. We can calculate FMA. Force is the same, 6 times 10 to the power 7. Same force that we used for airplane. So force doesn't change. We agreed on that based on the universal law. Mass change, 6 times 10 to the power 24. And then now we are interested to calculate the acceleration. Now suddenly you see different numbers. 6 and 6 will cancel. But acceleration becomes roughly 10 to the power 7 divided by 10 to the power 24 is equal to 10 to the power of 17. So we're going to have like this. So it's going to be like 0.017 zeros. And then 1. I missed a couple of zeros. So 17 zeros and 1. That's the acceleration of Earth moving towards the airplane. Very low compared to the acceleration of airplane moving towards the Earth. So conclusion. Based on a universal law of gravitation, any two objects apply a force towards each other, equal amounts opposite direction. That force of gravity, that force of attraction can be calculated using the universal law of gravitation. We made an example. Two objects, airplane and Earth. Earth has a mass of 6 times 10 to the power 24. Airplane has a mass of 5 times 10 to the power 6. Again, these are all assumptions. The distance between airplane and Earth was calculated as 6,001 kilometers. And then the G number, which is always the same, 6.67 times 10 to the negative 11. We made all the calculation and we found out that the force that is being applied both towards the airplane and Earth, they're both applying the same force towards each other, is equal to 6 times 10 to the power of 7 newtons. Very large number, a very large force. Now that force, surprisingly, even though it kind of doesn't make sense to us, but airplane is applying that force on Earth. It's actually pulling Earth by that force. And Earth is doing the same thing. It's pulling airplane towards itself. So both of them have this force applied on each other and against each other at the same time. Now the question is, if they're both applying towards each other, how come airplane is being affected by it, but Earth is not being affected? So now we made a calculation here. We said that the force is being applied on both, on Earth and airplane at the same time. But the effect of the force on airplane causes an acceleration of 11, enormously high. And the effect of the same force on Earth is enormously low. So airplane is pulling Earth towards itself And as a result of it, Earth is actually moving towards airplane, but with a very, very low acceleration, which is almost zero, which is almost not happened even before probably the airplane is moving and going around and just like finishes destination and even turned off and gone before even Earth feels an acceleration. You know what I mean? It's very low number. So that's why the acceleration on from Earth to objects it's very noticeable, um, and we can calculate it and we calculate the acceleration and everything with respect to it. But at the same time, we know that the Earth is being also affected by it, but that effect is very small because the mass of Earth is large, and because of it, the acceleration and effect become very low, which we almost kind of ignore. Okay, so this is a very good example because it tells us the whole story of what's happening in the equation. At the same time, we also talked about one topic in the beginning of our conversation, which we said because only in the questions and problems involving Earth. This is a very important point. Only if one of the objects that we've calculated in the gravitational field is Earth. For example, if you're calculating the gravitational force between apple and the book, which are two objects, whatever we're talking about right now doesn't apply. What we are about to say right now is only for Earth. If one of the objects are Earth, then the value of our equation could be summarized into some shorter equation. It could be summarized to 9.81 times the mass of the other object. It means instead of going through all these calculations to find 6.6 times 10 to the power 7, we could simply say that instead of all that calculation, I'm going to do 9.81 times the mass of airplane. What's the mass of airplane? 5 times 10 to the power of 6. If you do the calculation, this is roughly 10. 10 times 5 is 50. 50 times, so this is 5 times 10 to the power 7. I know it's not accurate, but it's very similar to what we got in the other calculation. Again, because we're making a lot of assumptions and rounding, so this one became 5 times 10 to the power 7. This one becomes 6, which is very close. Okay. So the force of gravitational between two objects, if one of the objects are Earth, only and only if one of the objects are in our situation is Earth, then the value of G and value of M1, value of R squared, in most of the cases becomes exactly the same number here we calculated, 9.81. So then we can kind of shortcut our equation to F equal to mg and calculate it in another way. If we do it very accurately with calculate and measure it, these numbers will be exactly the same because we're basically following the same numbers and same routine. Okay. So, any questions? Okay. If there are no questions, we cover so orbits. Okay. This is a very important lesson. Yes, that's what I'm looking into. But chapter 6 ends